So next test we're going to talk about in section 9.5 on page 21 of your notes is the ratio test. So there's two tests we're going to talk about in the next 2 pages. I'm going to call this the double R's because their comparisons are very similar. The ratio and the root have very similar comparisons. So the ratio test. So the ratio test, again, we had the ratio test for sequences. We're talking about series now. Again, we're still going to find the limit as k goes to infinity. I'm going to take u sub k plus 1 and divide it by u sub k. And these are the conclusions we're going to draw. When we find the limit, if it is less than 1, the series converges. If it is greater than 1, or it goes to infinity, the whole series diverges. So again, we have to calculate the limit of this. If it's less than 1, it converges. Greater than 1 or infinity, it will diverge. If the series is equal to 1, then the test is inconclusive. It may converge or it may diverge. So it's used commonly for factorials and exponentials, just like for the sequences. So use the ratio test to determine whether the following series converges or diverges. And again, the series has to have positive terms. So it does not apply if you have any negative terms or alternating. We'll talk about the alternating series later. So again, the condition to use the ratio test, all terms are positive. And again, since I'm starting at k is equal to 1, I know they are. So again, to use my ratio test, I know that u sub k is my given, the 1 over k factorial. U sub k plus 1 is equal to 1 over k plus 1 factorial. And again, just like with the sequences, I know I'm going to have to simplify this, so I can write this as 1 over k plus 1 times k factorial. So then to find, using the ratio test, I have to find the limit as k goes to infinity of 1 over k plus 1 times k factorial divided by u sub k, or multiply by the reciprocals. That would be k factorial over 1. So I can simplify this. My k factorials cancel out. So the limit as k goes to infinity of 1 over k plus 1 is equal to 0. And again, the conditions for the ratio test, if the limit is less than 1, the series converges. So since 0 is less than 1, the series is going to converge. So I have k divided by 2 to the k for example B. So again, u sub k is my given. U sub k plus 1 is equal to k plus 1 divided by 2 raised to the k plus 1. Again, remember, just like we saw with the sequences, I can rewrite 2 raised to the k plus 1 as 2 to the k times 2 to the first. So I need to find the limit as k goes to infinity. My u sub k plus 1 is at k plus 1 over 2 to the k times 2 to the first, divided by u sub k, which means I'm going to multiply by the reciprocals. That'll give me 2 to the k over k. Again, 2 to the k's will cancel. So I want to find the limit as k goes to infinity of k plus 1 over 2k. So again, the limit as k goes to infinity of this fraction is going to be 1/2, since the degree of the numerator and denominator are the same. So 1/2 is less than 1. So again, the conditions for the ratio test is the series will converge. So I know this is going to converge. So the next one, k to the k over k factorial. As k goes to 1 to infinity, again, all my terms are positive. So again, u sub k is equal to k to the k over k factorial. U sub k plus 1 is going to be equal to k plus 1 raised to the k plus 1 over k plus 1 factorial. So again, I can rewrite the numerator as k plus 1 raised to the k times k plus 1 to the first. All over, again, I know I'm going to be simplifying my factorials. This will be k plus 1 times k factorial. So then I want to find the limit as k goes to infinity. Again, I'm going to take my u sub k plus 1, which is k plus 1 to the k, times k plus 1 to the first, all over k plus 1 to the first, times k factorial. Divided by u sub k, which means I'm going to multiply by the reciprocal, so that'll give me a k factorial over a k to the k. So I can simplify. The k plus 1s will cancel. K factorials will cancel. So the limit, as k goes to infinity, I end up with k plus 1 to the k over k to the k. Now, you need to highlight this one because this is a limit that will come up over and over again, and no, it's not going to be equal to 1. I can rewrite this ratio because both the numerator and denominator are raised to a power of k. So I can write this as k plus 1 over k, and this whole quantity is raised to the k power. I can split what's inside my parentheses up. K over k is 1, plus 1 over k, all raised to the k. This is a very famous limit. It represents one of our famous irrational numbers, and this is the definition of where our little e comes from. The limit as k goes to infinity of 1 plus 1 over k raised to the k. This is approaching e, and we know that e has a value of about 2.7, so e is greater than 1. So since this limit is greater than 1, I know this series is going to diverge. So yes, definitely want to make sure you remember that limit. So here's another example. We have 2k factorial divided by 4 to the k. So again, u sub k is equal to 2k factorial divided by 4 to the k. U sub k plus 1 is equal to 2 times k plus 1 factorial over 4 to the k plus 1. Again, I can distribute this to give me 2k plus 2 factorial in the numerator. So I know I'm going to have to simplify my factorial, so I can simplify my numerator down to 2k plus 2 times 2k plus 1 times 2k factorial. I can rewrite the denominator as 4 to the k times 4 to the first. So again, using my ratio test, I want to find the limit as k goes to infinity of u sub k plus 1, which is 2k plus 2, times 2k plus 1 times 2k factorial, over 4 to the k times 4 to the first, divided by my u sub k, which means I'm going to multiply by the reciprocal, which will give me a 4 to the k over 2k factorial. So 4 to the k's are going to cancel, 2k factorial is going to cancel. So I'm left with the limit as k goes to infinity of 2k plus 2 times 2k plus 1 all over 4. So notice the degree of the numerator is a square. That'll give me a 4k squared on the top over my constant of 4. So again, this limit is going to be going towards infinity. So now remember the condition of the ratio test. If the limit is greater than 1 or is infinity, the series diverges. So this series is going to diverge. So again, like I said, if it's infinity, it diverges using your ratio test. So 1 over 2k minus 1. Again, using your ratio test, again, my u sub k is the given. My u sub k plus 1 is 1 over 2 times k plus 1 minus 1, which is 1 over 2k. 2 minus 1 is a 1. So then I want to find the limit as k goes to infinity. U sub k plus 1 is 1 over 2k plus 1. Divide by u sub k, which means I'm going to multiply by the reciprocal. So this is going to give me the limit as k goes to infinity of 2k minus 1 over 2k plus 1, which is just going to give me 1. Now remember, if you get this limit of 1, this tells you nothing about the convergence or divergence of the series. It's inconclusive. So what has to happen is you've got to pick another test. And some of you may have already chosen the test that you want. 1 over 2k minus 1 is a rational function, so you can use your polynomial test. So again, when you look at the series k is equal to 1 to infinity of 1 over 2k minus 1, the degree of the numerator is 0. the degree of the denominator is 1. So since 0 plus 1 is greater than or equal to 1, this is going to diverge by your polynomial test. So like I said, if you get a 1 using your ratio test, you have to pick another test. My other R test is called the root test. Again, the root test is when you have a series that is raised to the root. This power is not affecting the convergence or divergence of the series. In other words, we're just going to look at the limit as what's happening raised to that particular power. Again, the conditions are just like the ratio test. If your limit is less than 1, the series converges. If it's greater than 1 or infinity, the series will diverge. If it's equal to 1, the series may converge or diverge, so another test must be tried. Again, this can be used when your power is a variable and the terms are all positive. What's determining the convergence or divergence of the series, when you have this power, it's what's happening on the inside raised to the power that's determining the convergence or divergence of the series. Again, the power is your variable. So for example, make sure you have your positive terms, and again, your variable is a power. So I can apply my root test. So what I want to do is find the limit as k goes to infinity. Again, and I'm looking just at what's inside of the parentheses. 4k minus 5 over 2k plus 1. Degrees are the same, so I know this limit's going to be 2. So since 2 is greater than 1, by your root test, this is going to diverge. So looking at this particular series, I have 1 divided by the natural log of k plus 1, all raised to the k. I can write this fraction also as 1 over natural log of k plus 1, all raised to the k power. So I can apply my root test because all my terms are positive since I'm starting with k is equal to 1, and my power is a variable. So I can find the limit as k goes to infinity of 1 over the natural log of k plus 1. Again, as k is approaching infinity, the denominator is getting larger and larger. 1 divided by a really, really, really large number is getting close to 0. So since 0 is less than 1, then by your root test, this series is going to converge. So next I have the fraction e to the 2n divided by n to the n. I can rewrite this fraction as e squared over n, all raised to the nth power. So I can apply my root test. Again, all terms are positive, and my variable is a power. So I can find the limit as n goes to infinity of e squared over n. Remember, e squared is just a constant divided by a really, really, really large number. It's getting close to 0. So again, 0 is less than 1, so I know the series is going to converge. So for part D, I have 1 divided by the inverse tangent of n. Again, remember, just a reminder of what your graph of inverse tangent looks like. Remember, you have two horizontal asymptotes at pi over 2 and negative pi over 2. So again, the graph of inverse tangent looks like that. So to apply the root test, remember I can rewrite this fraction as 1 divided by the inverse tangent of n, all raised to the nth power. So I can apply my root test. So I'm going to find the limit as n goes to infinity of 1 divided by my inverse tangent of n. So like I just showed you, as n is going to infinity, what's happening with this inverse tangent? It's approaching pi over 2. So this limit's going to be 1 divided by pi over 2, or 2 over pi. We know pi is about 3.14, so 2 over pi is going to be less than 1. So then by your root test, this series is going to converge. So that is your root. That is your, I call them the double R, the roots and the ratio go together because the conditions are very similar.